In this unit, we've discussed discrete random variables. In general, a random variable is a variable that can take on several realizations, and each of those realizations has a likelihood of occurring. That is, the behavior that we're witnessing isn't constant. We see different behaviors over and over, where there's a likelihood associated with each behavior. Some behaviors are more frequent, some are less frequent. Random variables can come in a discrete form, where the realizations are discrete numbers, or in continuous form, where the realizations are measured on a continuous number line. The probability distribution of a discrete random variable lists all the realizations along with their probabilities. This could be in a tabular form or in a graphical form with a bar graph. A couple descriptive measures of discrete random variables are the expected value and the variance. The expected value is essentially the mean of the random variable, found by multiplying each realization by the likelihood that that realization occurs, summed across all realizations. The variance is the expected value of the squared difference between the random variable and the mean of the random variable. Some phenomena are best described with relative frequency. That is, establishing the probability distribution by looking at the past realizations and how often those realizations occur. And some phenomena are best described with functional forms of a probability distribution. We described 4 discrete probability distributions that have a functional form: the binomial, the hypergeometric, the Poisson, and discrete uniform distributions. There are others, but these are the 4 common ones. The binomial distribution described a situation where we want to know the probability of a number of successes in n repetitions of a Bernoulli trial which has one of 2 outcomes: success or failure. We know the probability of success of a particular trial, so we can count the ways that the number of successes and failures occur in n trials. Then we multiply the probability that that string of successes and failures occur. The hypergeometric distribution described a situation where we have a finite population of capital N, which is made up of 2 groups, successes and failures. There is some number of successes, R, that appear in the population. Therefore, there is some number n minus R failures that occur in the population. We then pull a sample of size little n out of that population, and we find the probability that that little sample contains some number of successes. The distribution sounds similar to the binomial distribution, but it's different in that the number of successes and failures in the sample are not independent of each other. Witnessing a success from the population alters the probability of witnessing another success, as there's one fewer success to pick from in that finite population. The third distribution we discussed was the Poisson distribution. The Poisson distribution can be used to describe situations where we have a rate of occurrence of successes per some interval. And we want to calculate the probability that we witness some number of successes during a randomly chosen interval. The rate of occurrence, lambda, is known. The final distribution that we discussed in brief was the discrete uniform distribution, which describes a random variable whose realizations are finite and equally likely to occur. We can use such a distribution to find the probability of a particular realization or a range of realizations. To calculate some of these probability distribution functions, we need an ability to count the number of possible successes. We discussed a few counting approaches to count the number of ways that an event that we're interested in can occur. The most common is the combination function, which counts the number of ways we can choose a number of R objects from a total number of n possible objects. With the combination function, we're only interested in selection without regard to order. If order matters, we use a permutation. Our discussion of discrete random variables sets us up to explore many different engineering applications, as well as head in the direction of continuous random variables in the next unit.